Alrighty, welcome back to 353. Yeah, a lot less people here than there were Monday. Kind of forgot how many people were in the class. So, today we talk about inodes to get back on track because we were talking about how a file is stored and how we would describe where the contents of the file are in terms of blocks. And where we left off, we had the linked list approach was basically the file allocation or FAT table. Then we argued that, hey, linked lists are silly. We should use an array instead. We left off, we'd use an array and use a block just to store that array of blocks that represent the file. But then we were like, hey, the file can't be that bad, so that's pretty lame. So we can fix that today, and I will just spoil everything. An inode is the structure in the kernel that describes where on disk a file is and all of the information about said file. So, remember when we talked about vnodes with file descriptors? Well, in terms of like regular files, the vnode it's referring to is actually an inode for regular files because this tells you where on disk things are. So content stored on the inode are like the mode of the file, so like, you know, all your permissions, everything like that. Who owns the file, the user and the group. Timestamps, like when you created it, when you last modified it, and when you last changed it, which are a slightly different thing. The size block count, so how many blocks does this file consume, and then some other information, and then here is like that array. So that array, what we talked about before, would be called a single indirect block. So it's just a pointer pointing to a block on disk, and this block is an array of pointers pointing to the blocks that store the actual data. So this might look similar to virtual memory. So the only difference here is we have different sizes. With virtual memory, it's just always 3 levels or always 4 levels or always 2 levels or whatever. Here, it kind of depends. So the idea here is there are a whole bunch of pointers stored on the inode itself, usually 15. And there are 12 of them usually reserved that point directly to blocks. So that if the file is small, it doesn't actually have to waste a block of data on the disk to store all its array. Small files can just have their block stored directly on the inode itself. If the file was larger than 12 blocks of data in this case, then for the next 13 and up data blocks, it would use a single indirect block, so it would get a block full of pointers, and then they point to data. And that's where we left off, where the file wasn't that big. So in terms to make it more flexible, there can be a double indirect block, which points to a block full of pointers, and each of those pointers to a block points to another block full of pointers, which again points to a whole bunch of data. And then if we need an even larger file, we can use a triple indirect, which is the same idea as the 3-level page table. So why it does this is because there's a trade-off. It aims to be efficient for small files and also support large files. So Unix inodes hold metadata and pointers to blocks for the most part. Smaller files only use direct pointers, so they don't have to waste a block on disk to store the pointers if it was just one big array. And then if you have larger files, they would have additional index blocks or index nodes with pointers to additional blocks. How many levels depends on how big that file is. There is also an optimization that very, very, very small files can have its contents directly stored inside the inode itself. Similar to most other optimizations in languages with strings. So if a string is small enough, it will be stored in the string pointer itself instead of it actually points to somewhere else on disk. So if you haven't heard about that, that's the small string optimization. Same idea here. So we can make it an inode problem, look similar to the virtual memory problems. So we could just say, hey, an index block, so an inode itself stores 12 direct pointers, one single pointer, or one single indirect pointer, one double, and one triple. And we could say, hey, a disk block is 8 kilobytes in size, just to make it, I don't know, more fun and do something different than 4 kilobytes. Then we could say a pointer to a block is 4 bytes. And then assume the indirect blocks or index blocks consist of direct pointers only. So then we can answer the question, what is the maximum size of a file managed by this index block? Or how many data blocks can it point to? Well, in this case, we can figure out, just like with virtual memory, how many pointers can we store on a single block, so in a single indirect table. So it would just be the size of a block, which is 8 kilobytes, otherwise 2 to the power of 13, divided by the size of a pointer, which is 4 bytes, which is just 2 to the power of 2. Then we can do our math and figure out that we can store 2 to the 11 pointers on a block. So in total, given that scenario, the number of addressable blocks we can actually use for the file is, well, we can use 12 from the direct blocks, because they just point directly to a block we can use for data. Then through the single indirect block, we have 2 to the 11. And then for the double indirect block, it's 2 to the 11 all to the power of 2. And then for the triple, it's 2 to the 11 all to the power of 3. If we want to just estimate it, this term will dominate all the other ones. You can calculate it out if you want, but it will be approximately equal to 2 to the 33. So the total number of bytes we can actually use as the maximum size of our file is 2 to the 33 times the size of a block, which is 2 to the 13 in this case, which is 2 to the 46, which is 64 terabytes. So a single file can be 64 terabytes. So that should keep us happy for a while. And if we wanted to easily make it so that we could store a file, 2 to the 11 times bigger than that, what would I have to add? Yeah, quad indirect block, and then boom, we're done. And just figure it out from there. But this is what we use right now because no single file really is more than 64 terabytes. All right. So to store, we can actually start talking about how to actually read the output of ls now, which you don't really know how to do. So hard links, there is something called hard links on your file system, and they are just pointers to inodes. And a hard link is just a name to an inode, just so you don't have to refer to the contents of a file as, inode 2658. You just say, hey, I want to refer to it as to-do.txt. So a hard link is just a pointer to an inode. And this is what is in a directory. So a directory entry, aka a file name, anything in your directory, any file you accessed, is technically called a hard link. And a hard link just points to one inode. Okay with that? All right, so, well, if there's something called a hard link, you might imagine there's something called a soft link. But before we get to that, multiple hard links can point to that same inode. So I could have to-do.txt and b.txt both pointing to the same inode. And this is why that rm command doesn't actually delete a file. It doesn't actually remove anything. So deleting a file or using the rm command only removes a hard link. The file can still be hard linked somewhere else. So if you strace rm, you'll see that it doesn't, there's no system call called rm or anything like that. It's just called unlink. So it just removes that name. So, ooh, echoey. All right, so why are you doing this? All right, so now let's create a file called, so let's touch a file called a.txt. The touch command will just create an empty file with that name if it doesn't exist. Otherwise, it just updates the timestamp of when you've last modified it. So if I do that, and we've all done ls-l before, right? So let's go through all of these because we should be able to explain what they all mean. Anyone tell me what that means? Permissions, right? Specifically, that's like user permissions, so what whoever owns this file can do to it. Then group permissions, whoever is in that group that can do with do with it, and then other permissions if you're not that owner or you're not in that group. And then this is the username of the owner, so the user, and then this is the group name of the group that owns that file. All right, what about this? 1. You've been using ls for how long? You don't know this first number? Any guesses? All right, well, let's skip that then. So these we just went over. What's this number? File size, right? So let's say I just try and edit the file, and I go, hello, and that will also tack on a new line. So if I do this now, I can see the size of the file is now 6. So hello, and then it added a new line at the end of it, not a null byte or anything like that. So that is the size of the file. All right, what is this? Yeah, last modified date probably, and then the name of the file. So no one knows what this number is, right? All right, here, let me add another thing. All right, so if I do -li, I have a new number. Anyone guess what this big number is? Yeah, that is the inode number. So how to actually create a hard link, which you probably have never done before, is the command called ln. So if you use ln, that will create a hard link. And if I do something like a.txt, b.txt, this is the new name that is created, b.txt, and it will actually make it so that b.txt's inode points to the same inode as a.txt. So if I do that and just run ls, I can see that, hey, I have a a.txt and I have a b.txt. So if I run ls-li again, anyone guess what that number is now? Yeah, the number of hard links to that inode, right? So you can see both of them. I have a.txt and b.txt, and these inode numbers are the same. So this is the inode number, and there are 2 links to it. So if I want to get more information about a file, I can use stat. So if I do stat b.txt, it'll tell me a whole bunch of other information. So size 6, blocks 8, seems a bit weird. We'll get into that in a little bit. What the size of an I/O block is. It's a regular file, what device it's on, what inode number it is, number of links it has, so that's number of hard links, and then access, some weird permission stuff. Access, modify, change, and birth. So birth is just created. Access is when you've last accessed it. Modified is when you've last modified the contents of the file. And change is when you've last done something to the inode itself, which is slightly different. So that changed. I didn't actually change the contents of the file whenever I made a hard link to it, but I changed the inode itself because I increased the number of links from 1 to 2. So that is why those numbers are slightly different. All right, so the contents of my a.txt were just hello. If I cat b.txt, what am I likely to see? Same thing, right? Hello. So now, without modifying file A, if I just modify file B and say hello class and say I'm yelling. So if I do that, what should I see if I cat a.txt now? The modified version. Yeah, the modified one, right? So if I do this, even though I didn't change a.txt, I see hello yelling class because, well, the inode itself is storing all the information about the contents of that file. If both a.txt and b.txt are pointing to that inode, if I change the contents of the file through either one, I'm changing what that inode refers to, and it will update both of them. So That's also a fun way to confuse, people that haven't taken this course. Just create a bunch of hard links to everything and tell them to, just create a bunch of hard links to everything. Yeah, and then we can see here that indeed, if I just do rm b.txt, I can see that, hey, I still have one link to the file, or one link to that inode. So this doesn't do anything. That doesn't actually delete anything, right? So the only time something may be deleted is if you decrease that count from 1 to a 0, then it's not referred to by anything, then it could be deleted. So spoiler alert, this is also basically how your recycle bin works. So your recycle bin will just keep a hard link to that inode so it doesn't get actually deleted by the operating system. Keep it around for 30 days or whatever that is. And that's why restoring is also really, really fast, because it just recreates a name that points back to that inode. So even if you delete a 10 terabyte file, it will restore instantly, because it's just creating a name to an inode. That inode, you're not copying anything, you're not doing anything like that. It just, you just recreate that name pointing back to that inode. You always just save a reference to it. So that's what your recycle bin does. All right, any questions about that or any other fun stuff you want me to do with that one? All right, cool. So, yeah, there's soft links. So, soft links are paths to another file. So, when resolving the file can be redirected somewhere else. So, a soft link, the way I like to think about a hard link is a name to an inode, while a soft link is a name to a name. So, technically, there's an inode so technically, this is a soft link or symbolic link or shortcut, whatever you want to call it. And the contents of that symbolic link will be stored on inode itself. But when you try and access it, the easiest way to think about is a name to a name. So when resolving the file system's redirected somewhere else. So because of this, you can create loops and all sorts of fun things. So soft link targets do not need to exist. Their targets can be deleted without notice of the soft link. So if b.txt points to to-do.txt and I get rid of to-do.txt, that's fine. It will just be unresolvable, and they might lead to an exception or some type of error. So how we create soft links is the same way we create hard links. So this is how we created without the -s, this is how we created a hard link. If we want to create a soft link or symbolic link, or in Windows land, a shortcut, we just do -s. So if I do, other way around. So I want to create a file called b.txt that is a symbolic link. So b.txt should essentially point to a.txt. So if I do this and do ls now, I can see that, hey, this is how it displays a symbolic link to me. So there's a symbolic link called b.txt that points to a.txt. And that's the way to think about it. If I look at the inode numbers, I can see that it by itself is stored on an inode. So this content, which is a.txt, needs to be stored somewhere. So it's stored on this inode. But in terms of using it, easiest way to think about is a name to a name. So if I cat b.txt, I'll see hello class, because it will go from b.txt, be like, oh, okay, well, I need to find whatever inode a.txt refers to. And then, okay, well, that finally points to an inode. I'll use that from the contents of my file. So now if I remove a.txt, I can see that it doesn't really show anything. It just, b.txt goes to a.txt. Any guesses what will happen if I cat b.txt now? Yeah, it probably shouldn't work. Might give us a weird error. So if I do that, I guess it's a very weird error. It says b.txt, no such file directory. which is a bit misleading because b.txt does exist. But what it's trying to point to, a.txt does not exist. So other fun things we could do, you might imagine we could create a loop. Like what happens if we do, I don't know, let's say we create a file called a.txt that points to b.txt. So we could do that, right? Nothing prevented it from doing us. Any guesses what will happen if we do something fun like that? Yeah, infinite loop, right? So it's like, hey, to get the contents of a.txt, I need to go to b.txt. To get the contents of b.txt, I need to go a to b, b to a, so on and so forth, infinitely. So if I run cat a.txt, any guesses what will happen? Should infinite loop, so either should get an error or it crashes. So if I cat it, I'll see, ooh, they're smart. Says, error, too many levels of symbolic links. If I wanted to figure out who is smart, because either cat could be smart, right, where they detected it, detected a loop or something like that, or the kernel could be smart, where it detected a loop or something like that. If I wanted to figure out who the smart one was, how would I do that? Fun tool you should use that works for every single programming language. Did I hear strace? I heard strace. So we can see what the cat program does by running strace and see who is smart, the kernel or whoever developed cat. So if we run this, we can see that, okay, this is a write to standard error, too many levels of symbolic links. Had to open some locale stuff so it could display my message. Go up to the first thing. So this is also just writing part of the error message in parts. Oh, there it is. So it only did one open system call of a.txt, and it got an error from the kernel. So the kernel gave an error code eloop, too many errors. So kind of makes sense that you didn't know this was a possibility before probably this lecture. So kernel takes care of it for you. So your program, you just don't have random infinite looping programs because that would be very bad. All right. Any other questions or fun things you want me to do with this? All right. Well, I can show you something that is totally why I trust file name permission. So has anyone ever argued with their professor something like, hey, I was done my assignment on time. Here's the timestamp of the file. Trust me, bro, I definitely did this, right? People have probably done that. Might notice at the bottom of the lab docs, it's like, I don't trust your times. Because guess what? This touch command, it can just update times for you. So if I did something like this, touch, you can just set the modified date because that's just stored on the inode itself, right? Doesn't matter, you can modify it, do whatever you want with it. So let's say I want to change my modified date of c.txt to Christmas Day, 1980 at 6 a.m. And I'm not that old, I was not alive then. So if I do this in ls, whoops, ls-l, see that, hey, yeah, there's my modification date. I submitted it on time, trust me. So I did not show you how to do that, but someone I know may or may not have done that, and it may or may not have worked. So if you're, actually, no, I should just shut up. I'll probably get in trouble. So people should not trust your modified date because you can change it to whatever the hell you want. So store it on the inode itself. Even if you couldn't do this, I mean, like with games and other stuff, just set your system time to whatever you want. and it trusts that. So yeah, timestamps you don't control don't mean anything. So I don't know why I showed you that, but whatever. So there could be little problems like this, file system example problems that ask you what does the file system look like here before and after some commands. So if we do something like touch todo.txt, that will create a new empty file called todo.txt that would get its own inode. Here, ln todo.txt, b.txt, so this would create a new hard link called b.txt that points to the same inode as todo.txt. And then if we do ln-s, that is a soft link or a shortcut. So we're going to make something called c.txt that points essentially to the name todo.txt. So the question is, what does it look like before and after the move and rm commands? So before this move command, before I do anything, it should look something like this, right? So if I have inode 1, which was created when I created todo.txt, created another hard link called b.txt that pointed to that same inode, and then I created a soft link called c.txt that points to todo.txt. And again, this is more of a way to visualize it because c.txt will, there's an inode in between here, so the contents of c.txt, which are todo.txt, is stored itself on an inode. So there's actually an inode in between here, but we don't really care about that in terms of understanding. Just draw a soft link as a name to a name, and then a hard link as a name to an inode. So if we do mv, you might have heard it called move, but that's a pretty poor name because all it does is rename the directory entry. Probably, well, they decided against calling it rename because that looks an awful lot like rm, which is remove, but that one doesn't actually remove anything either, so I guess both the names are kind of misleading. So if we do move, which doesn't move anything, all we're doing is changing this name todo.txt to d.txt. So we change, so todo.txt, which was referring to inode 1, is now got renamed to d.txt. And this todo.txt is only referred to by the soft link c.txt. So it got removed from the directory. We wouldn't see it if we did ls. We would only see c.txt, b.txt, and d.txt. So if we tried to access c.txt, we'd get file not found c.txt. So if we do rm b.txt, well, that just removes, or that just unlinks, gets rid of the name b.txt, so we still have something referring to inode 1, and it wouldn't actually get deleted or anything like that. So any questions about going through that? Wow, today's going to be fast then. All right, so in Unix, everything is a file. Directories are actually files of type directory. So additional types are, they can be regular files as well. Symbolic links, which I didn't put here, but that is a different file type. Block device, so like hardware gets represented as just a file. So HDDs and SDDs. Pipes can get represented by files, sockets, which we saw, and a whole bunch of other things. So directory inodes do not store pointers to data blocks or anything like that. It just stores a whole bunch of name inode pairs. So if I go here and I look at this and do -li, so there'll also be an entry for dot and dot dot. And dot refers to the current directory. So its inode is, I don't know, this, I'll just call it by the last two numbers. So the current directory is inode 78, and the parent directory is inode 51. So if I go backwards and I go up a directory to the parent directory and go here, I'll see that, hey, 78 is what's called test in this directory. So in this directory, well, that is the contents of the test directory. So this inode number and this inode number are the same. Makes sense. And then this directory here, which is called 18-inodes, is inode 51, which makes sense because it's the parent of this one's directory. And should be noted here that just because of this file system, this number is actually just 1 for all directories. On some file systems, that would not be true. So if it was on a slightly different file system, this number might be actually 2 because it's referred to by dot in this directory, and then it's referred to by test in this directory. So technically, the number of links to it is 2. Just happens that the file system I'm using on this machine now just displays all directories as just having 1 link to it, even though it's not technically true. All right. Any questions about that? We finally figured out what the hell that number means. So it took until 3rd year to figure out what LS is telling us. All right, so we can do quick little quiz or just quick little what's stored on an inode. So if we go through the list, what's stored on inode? The file name, not stored on the inode. File names are only stored in directories. So the contents of both directories, so there'd be a whole bunch of data stored for this directory, but all it stores is name, so dot, and then inode pairs. So it would just store dot 78, dot dot 51, a.txt 75, b.txt 67, and c.txt 87. So that would be the entire contents of that directory. It just stores a whole bunch of name inode tuples. That is all that a directory is. So the file name itself is not stored in the inode because, well, also you can have multiple names referring to that inode, so they're not stored there. Also, it does not know what the containing directory's name is. In fact, because multiple names can refer to that inode, they don't even have to be in the same directory. What is stored on the inode is the file size, so how many bytes of the file are actually valid, how many bytes of the block does it actually use for the contents of the file. File type is also stored on the inode, so telling you information about the file. The number of soft links to a file, not stored on the inode itself. It's just a name to a name. Doesn't get updated. If you remove it, it's fine. And similarly, the location of soft links aren't saved anywhere, or sorry, they are saved on the inode itself, but you'll get experience with that in the lab as well. And then the number of hard links to a file is stored on the inode itself. Basically, minus the file name, whatever you stat about the file, that's stored on the inode itself. The location of the hard links are, again, not stored on the inode itself, but it does store access rights, timestamps, which you can definitely not modify. And then the file contents aren't stored on the, well, sometimes they'll be stored on the inode itself in special cases, but it's pointing to where on the disk the file contents are. And then it also has an ordered list of data blocks because that is the whole point of an inode. So just to make sure that we're not crazy, these are all the answers to them. So that is all the answers to them. Again, just what we went through. So the file contents only says sometimes because of that small optimization, and that's only true for symlinks, but again, you'll see it on the lab. So any questions about anything we went over today? Inodes, big fun, yeah.
So if the drives are also represented as inodes,
yeah.
does the size limit also apply?
Is the size limit?
Yeah.
Let's see. So the drives on your, on your system, they'll be represented in this dev thing, this dev directory, which isn't real. And you'll see that, hey, there's a whole bunch of things here. They're all in yellow, and this B here means they are block device, so they can only be accessed blocks at a time. I haven't explored this one yet. Let's see. It should be called stat dev SD. NVMe. Okay, I'm using a virtual machine. I'm not sure what my hard drive is called. Let's see, LSBLK. Okay, so this will tell me the name of my devices and where they are mounted in my file system. So the name of the disk I'm using is VDA, apparently. So if I stat dev VDA, that is the inode that represents my, well, the vnode that represents my disk. And if I look at it, I can see that, hey, it says that, hey, there's no blocks. It's a block special file. Tells me what the block size is, but it doesn't actually contain any blocks or anything like that. Doesn't give me any useful information. So there'll be like special system calls you can use that say, hey, how big is this disk and everything like that. But if you want to like access a disk just straight up, you can use that special file to access that disk. Or if you like try to flash a USB drive, it will appear as something like that, and you can go ahead copy stuff to it. All right, any other stuff? So that was slightly on the fly. All right, oops. All right, so other little fun things. So file systems have caches that speed up writing to disk. So writing data to a disk is slow. We can use a cache to speed it up. So file blocks, so the actual blocks that represent the file, can be cached in main memory, especially really easy if they're the exact same size as a whole page of virtual memory. And typically the kernel will have something called a file system cache, where it will actually, if you go ahead and update the contents of the file, it won't actually write it to disk because that would be slow. So it just keeps that disk in memory because likely if you've referenced a block or if I modified a file, you're likely to modify it again. That's something called temporal locality, which is properties of caching that make caching great. And then logically, near blocks are likely to be reference a spatial locality. So if I'm modifying a big file, likely I'll be modifying the next few contents of the file as well. So any changes you make to the file, they'll just be only represented in main memory. And then a kernel thread or daemon process or anything like that will just write changes periodically to disk. So when you save your file, doesn't mean it's actually saved to disk. So if you lose power or anything like that, well, you may actually lose work if it's been cached, if it hasn't actually been saved to disk. That's what the flush and sync system calls do. They make sure that all the writes in the file system cache actually occur. And I've had this happen to me when I was trying to set up a USB boot drive. I knew the USB drive was slow. I copied a Linux ISO to it, and it was done way too fast. So if you ripped out the drive, it would be corrupted. And then I was like, oh, okay. Well, then I had to run the sync command, so you can just do sudo sync. And then it took a long ass time because, well, USB drives are slow. But after that, it was done. I could pull it out, no problem. Also, you might have noticed flush also works for your standard file descriptors. Slightly different because printf itself will cache things to reduce the number of write system calls that happen. So same idea is the same. There's a cache. If I want to make sure something actually happens, I have to flush the cache or sync it or whatever you want to call it. All right. Speaking of maybe losing data, like I said, because of the file system cache, you delete something or you modify something, might actually not be reflected on disk, especially if you lose power, files get corrupted. Probably not a good thing. So there is something called a journaling file system, because deleting a file on Unix, if we take that as an example operation, it takes 3 steps. Right? I have to remove the name from the directory entry as the first step. So I remove that name to inode link. Then, well, if that's the last thing referring to that inode, well, then I can free that inode, right? That inode can be reused for a different file. So I would have to release that inode back to the pool of free inodes, basically deallocate it. And then any disk blocks that file used, Well, they're not used anymore, so I can return them back to the pool of free disk blocks. And, well, between any of these 3 steps, right, if we wanted it to happen thread safely, we could put a lock around these 3 steps, make sure they all happen safely. But one thing you cannot protect against is, someone yanking the power cord out between these 3 steps. Lock isn't going to help you at all there or anything like that. So if I crash between, step 2 and step 3, then that inode looks free. It's not referred to by anything, but all of the disk blocks it used will be marked as used on the file system, even though they are not used at all. So before journaling file systems, you'd have to scan the entire file systems, look for integrity checks, look for things like that where some things aren't referred to. It's going to take a long time. That's what FS check is, file system check, basically what it'll do. But if you have a journaling file system, basically what the journal will do is before starting these operations, it will just record what it is doing. So it'll be like, I'm going to delete a file, then write it to disk before it starts deleting the file, and then it will start doing the 3 steps. And then if it crashes or power gets removed between any of these steps, it can look at the journal and be like, hey, I was in the middle of deleting a file, so I should go back, replay those 3 steps, and then I know what I need to do in order to make the file system correct again and consistent. After you've done all these 3 steps, you would remove that entry from the journal and say, hey, I've done this, it completed successfully, so there's no problem with this operation. So that's basically what the journal is. Its name is not creative. You just record what you're about to do the operations. If you successfully do them all, you cross them off the list. If you crash and you look at the journal and there's things not crossed off the list, then you go back, look through it again, and fix it. So what we learned today, inodes, they are a hybrid allocation strategy. So they offer greater flexibility over what we explored before. Contiguous linked file allocation table, or FAT, which is basically just linked, or indexed, which just used basically a single indirect block. Oops. So on Unix or POSIX systems, so Mac OS or Linux, everything is a file. Names in a directory can either be hard links or soft links for the most part. So with that, I will hang around the extra 8 minutes. You can tell this course is starting to get, thankfully, easier now. So we have made it past the hump. All the topics from now till the end are, well, let's not say easy, but they are considerably less difficult. Let's say that. So we made it over the hard part of the course. So congratulations if you did not drop the course now, because it is now too late to do that. So just remember, pulling for you, we're all in this together.